Let's see how to set up a double integral in polar coordinates. Here we want to find the double integral of the function x plus 2y over this region, which looks like 3/4 of a circle of radius 1. So anytime your region looks like a portion of a circle or a region that's between two circles, that's typically a good time to use polar coordinates. Because, for example, if I wanted to slice this thing vertically or horizontally, I'd have to end up splitting the integral into two pieces, because some vertical slices would start on a circle and end on the same end on kind of the opposite side of the circle, whereas some would start on the x-axis here and end on the circle. So that makes those not great choices for vertical slicing. Okay, well, in polar coordinates, this is an easy region to describe. So your range of r values, you just imagine rays kind of coming out from the origin. So instead of vertical slices or horizontal slices, it's now radial slices. And every ray out from the origin, well, it starts off in my region because the origin is part of the region, and it leaves when it reaches the boundary of the circle, which is r equals 1. So the range of r values here is from 0 to 1. And then the range of theta values is just where do I need to shoot radial rays here in order to hit every point in my region. And in this case, I start at an angle of 0. And as I work my way all the way around, well, I need to shoot rays in the first quadrant, the second quadrant, the third quadrant, all the way up until the negative y-axis, which is an angle of 3 pi over 2. So those are the inequalities that define this region. And what we have to do now is to convert this function to use polar coordinates. Remember that x is equal to r cosine of theta, and that y is equal to r sine of theta. dA gets replaced with r dr d theta. And since dr is on the inside, we put the bounds from 0 to 1. And since d theta is on the outside, we put the bounds 0 to 3 pi over 2. Well, let's distribute that r before we forget. And then we'll be able to do the integral from there. So you end up with r squared cosine of theta plus 2r squared sine of theta. On the inside, we integrate with respect to r. So you'll have 1/3 r cubed cosine theta plus 2/3 r cubed sine of theta from r equals 0 to r equals 1. So that's going to give you just 1/3 of cosine of theta plus 2/3 of sine of theta. So that's what that inside integral gets you, that function of theta. Okay, so once you've done the inside part, now we can go back to the outside integral. Integral from 0 to 3 pi over 2 of 1/3 cosine theta plus 2/3 sine theta d theta. The integral of cosine is positive sine, and the integral of sine is negative cosine. And now we just plug in our bounds and see what we get. So when you plug in 3 pi over 2, sine of 3 pi over 2 is negative 1. Cosine of that is 0. And when you plug in 0, sine of that is 0, and cosine of that is 1. So what do we have? Negative 1/3 minus 0 minus the quantity 0 minus 2/3. So that'll be negative 1/3 plus 2/3, so positive 1/3.